In Chapter 8, we're going to be trying to find a motif in DNA. And so we're getting more into sequence similarity. We've already talked a little bit about, for instance, tetranucleotide frequency, GC content. These are ways of determining if two sequences are similar. We did the Hamming distance. And so now we're going to try to find an exact match of one subsequence inside of a larger sequence. And if you look at the subs challenge on Rosalind, you'll see some pretty interesting, very mathematical computer science kind of a description of the problem. But it's pretty straightforward. Given a string like this, we're trying to find a string like AT, and the output should be the positions where that can be found. And so if we, in this, we're going to be looking at a few functions like str.find, which we've already looked at, and str.index. We talked about index in the last chapter. That works. There's also a list index that works very similar. And we're going to be talking more about string slices. We talked a lot about slices in the previous chapter. We're going to use sets to create a unique collection of elements. We haven't used a set before. We're going to talk more about higher order functions and how we can combine them. And we're definitely going to be looking at k-mers, which we talked about in the last chapter, as a way of finding subsequences. K-mers are, by definition, subsequences. And we're going to talk about how overlapping sequences, how to find overlapping sequences when we're using regular expressions. It turns out it's not that straightforward. So to start off, be in the top level directory. Make sure you do source bin, source v and v bin activate. I like to have two windows open, so I'm going to do that, and then I'm going to go into the 08 subs directory, cd 08. And from there, I'm going to copy the first solution to subs, copy solution 1, and it's going to be called subs.py, and we're going to look at how this is supposed to work. It's going to take two positional arguments. I hope by now you are very comfortable with how to use argparse to define that. And given the input, like we saw on the Rosalind page, we should get the output that we saw from there, 2, 4, and 10, and that matches 2, 4, and 10 given this input string in that subsequence. And that is how our program should work. I definitely recommend that if you feel like you know how to figure this out, you should go off and write a solution, write as many different kinds of solutions as you can come up with, and then come back and see how I went about it. And if you found a different way from me, I'd appreciate it if you send me a note. So here we're seeing here in this figure that the subsequence AT can be found at 3 different places, and it's very important that 2 of them overlap with each other, and that's going to be important for when we talk about the regular expression solution. So how do we do this? Well, let's start from scratch, always. I'm going to open up my subs. I only want 2 positions. I'm not going to need need text IO. I'm going to have a, let's see, what do I call them? Seek and subseek. So I call this seek, and I'll call this subseek, and I don't need the other arguments. And they're going to be positional. One of them is going to be sequence, and I guess I'm going to call that metavar. I'm calling it seek. That's fine. And this will be the sequence. And then this is to be positional, so it'll be called subseek. I don't need the long one. Let's see, the help, I'm going to call this subsequence. And I'm using subseek for that. I don't need to define the default or say that it's required. So a note here that it doesn't matter the order in which you put the other keyword arguments here. Metavar comes first and then help and metavar. It does not matter. The important thing is how I'm defining it as a positional argument, because it does not have any leading dashes. And so I'm going to parse those out. I'm going to say, seek is equal to args.seek, and subseek is going to be equal to args.subseek. And that is how I'll get started. I always like to just maybe start off by printing args as a fine place to start. And let's go run this. I'm going to run it the way that I did here previously with those inputs, and just verify that I'm seeing the correct. So part of what I want to be teaching you here is the process of writing a script and how I've written something simple, and I have a basic structure in place, and I run it and I verify that it looks like something reasonable. And even at this point, I can run PyTest and see what that I'm passing a couple of tests. Always the first one is that I've actually created the right program name and that it produces a usage. So if I at least start with new.py, I'm always going to pass at least one or two of the tests. So that is what I'm showing here. And so let's talk about how to find the subsequences. So again, I'm going to get back into my trusty REPL here, and I'm going to assign my variables to some values, to those testing values that we're using. Subseq is going to be equal to AT, and we're going to talk about some ways of finding this. So in the last chapter, I talked about using in. We were looking for the stop codon, the stop protein symbol in a list to know where to stop the translation of RNA to protein. And so we can do the same thing for substrings inside of larger strings. So I can say, is it true that subsequence is in seq? And it is true. And so that's good information, but I don't know where it is. And so I can say seq.find subseq, and it tells me it's at position 1. That is great, but I know it's in 3 positions. So how can I find the other ones? And the other thing too is I know that the first answer should actually be 2. And so here the Rosalind is expecting me to give in 1-based positioning. So starting counting at 1, and here in Python we're working with 0-based offsets, so I'm going to need to add 1 to pretty much every solution in Python to create the output that Rosalind expects. So that's useful, but I need to find 2, 4, and 10. And so how can I use find to do this? And so this is something an AI agent is not going to do. It's not going to read the documentation for you. You're going to need to read the documentation by calling help on str.find, and you'll find here that it takes some optional arguments. So just as with the command line, the optional arguments are in these square brackets to tell you they can be left out. And so string find requires at least a substring that looking for, but it also has an optional second argument, which is where to start looking, and then even an optional third argument, which is where to stop looking. So that's really useful. And one of the things that we notice here is that on failure, it's actually going to return -1 instead of an exception. So if, for instance, looking again, this is our seq. If I say seq.find, XYZ, it does not create an exception, which is excellent. Index, however, does create an exception. So we want to stay away from index. We want to just use find for this solution. So if I know that seq.find of subseq finds an answer at 1, then I can tell it to start counting at the next position, and it finds 3. And then I can start counting at the next position from there, and it finds 9. And those are the answers that I need if I add 1 to them. 2, 4, and 10, 1, 3, 9. So given what I just showed you, I highly encourage you, if you haven't already, stop the video and write a solution that uses this information. Write a little iterator that keeps track of where to start looking and print out those numbers. And the answer will mean so much more to you if you find it yourself And it may seem trivial. You may think, well, there's no point in me doing that. But, you know, I think I mentioned before that a binary search is actually a pretty straightforward algorithm, but I believe it took several publications of the algorithm before somebody got it right. I think the first couple were flawed. So I would encourage you, go figure out how to write this. Oh, and the most crucially, how do I know when to stop? Well, take that 9, add one more, and you see it returns -1. Well, now I know I'm done. The other thing I could probably do is just tell it to go up to the length of the sequence. So and here I'm showing another option is to use str.index. So I'm going to encourage you to try to come up with a solution using str.index that avoids creating an exception. And you can do that if we say if subseq in seq, then I want seq index of subseq. And it tells me 1. And so if I use the same idea using a string slice, I can say, well, first off, let's take a look at, so seq starting at 2. What does that look like? So it cuts off, if we look at seq, then if we start at 2, then it's starting here. And so we're saying, okay, go up to this point and give me the slice of that starting at 2. So just the way that we can use string list slicing, we can do the exact same operation on strings, which is kind of interesting. So I can say if subseq is in seq starting at the position after where it was found before, then I want to know what seq index of where is it found in using subseq 2. And it shows me 1. I'm getting a little bit confused here. So I was a little bit confused by this in the book. Actually, I think I have discovered an error here. What I mean to say is if the subsequence is in seq starting at 2, then tell me what is the index of subsequence in seq starting at 2. So actually that's incorrect. This is the correct way to write that. So if we read help on str.index, then we find that just as with str.find, there are 2 optional arguments. So there's a start and an end. So knowing that, I could rewrite this if let me just go back and say if subsequence is in there, what I want to know is the seq index of subseq starting at that position. And it tells me 3. And then I can use that information starting at the next position, tell me what it is starting at 4. And you can see that we're building up, and then when we say let's just say subsequence, let's do the test. Is it in there starting at 10? It is false. So then we would not execute this line here and therefore raise the exception. So there is another way to go about. It's very similar to what you saw with str.find, but I would encourage you to try to write a solution using that approach. The third way is to use k-mers, which we talked about in the last chapter. So you have code that you can now go back and pull in to find all the k-mers. I had written a codons function that you could modify. Now you want to find all the overlapping sequences. So I'm not going to show that here in the REPL. I would just say go back to chapter 7 and pull that function out and see if you can figure out how to do that. The final solution that I would encourage you to investigate is to import the RE for regular expressions. We've talked just a little bit about this. And there is, if you say help RE, there's a handy function called find all. And it will return a list of all non-overlapping matches in the string. So that's very important. If we say re-find all, and it is you're looking for the subsequence, that comes first in the seek. And we find 2. Okay, first off, we want 3. And the second thing is it doesn't tell me where they are. So find all is cool, but find iter is actually the function that we want. And now we see that that is a callable iterator object. We know, for instance, that if we were to assign this to a variable, and if I look at the type of found, then it is a callable iterator. And if you remember, we can call next on iterators, and it will return a match object. And it tells me here that the span is 1 to 5. That's where it's found. So that's the position 2 that we're looking for. If I call next again, it finds position 9. It skips over the one that was found at 3, though, because that's an overlapping match. And so if I call next again, then we get an exception, a stop iteration. So I have now exhausted the iterator. So if we do a for loop, it doesn't raise this exception. Another way of getting those, as we know, is to force that, is to coerce the iterator into a list, and it will then print the 2 matches that it found. But the problem is that there are 3. So I'm going to leave it to you to do some searching and figure out how can you find overlapping matches using regular expressions. All right, so I'm going to show you my solutions. They're all going to use the exact same get args that we had before. And my first solution uses str.find. So if I need to know the last position that something was found. So really this is where I'm starting. I'm going to call it last. And I'm going to initialize this to 0, which is the start of the string. And for everything that's found, for the positions that are found, they're going to go into a list that I'm calling found. And I'm going to establish a infinite loop. This is very common in a lot of programming techniques. And in Python, there are a couple of different loop operators. One is called for. We've seen that for some value in a list of values. And another one is called while. And the while wants to execute while something is true, while some condition is true, a predicate. Well, if you just do while true, you've now got an infinite loop. And let's look at our subs.program here, and I can prove this by just saying while true, print hi. And let us run our program. Let me open a third module, terminal. I'm going to first source v&v bin activate, and then I'm going to go into my AO8, and then I'm going to execute my subs, and it wants A and B. That's fine. And so we are now just printing hi, and that is, it will do that forever. So there's nothing to get out of this. The way, and we've seen this before, there's something called break. So if I put in here break, then it will only run one time and print one hi, and then it breaks. So using these ideas, how can we need to have a condition when we break out of our loop, otherwise we have an infinite loop. So we call seek find, is the string, so args.seek is a string, and on that I can call the find function to look for args.subseek starting at the last position. The first time we call this, it'll be set to 0. If the find returns -1, that means we no longer find the position, and so we break out of the loop. If we don't break out of the loop, then we have a position that we now can append to our found list, but we want to make it be 1 greater than what we've had. Because that's we don't want 0-based offset. We want to start at 1. And then we're going to set last to that position, to the next position, so that we don't find that position again. And finally, we need to print those. So let's take some of these ideas. I want to show a couple things real quick. If I say last is equal to 0, found is equal to the empty list, while true, position is equal to seek.find, because I'm just using the seek that's in here. Look for the subseek starting at the last position. If the position is equal to -1, then break. Else we're going to, and I don't need to say else because we will simply break out of this, and we will never actually get into the else. So if otherwise we want to found.append the position +1. And then I want to set last is equal to position +1. And finally, I want to look at found, and I see there's 2, 4, and 10. And so if I try to print found, then I'm going to print a string representation of a list, which is not what I want. But there's something funny about, so if I just look at found, that's basically the same thing that I see. It's printing a string representation. I can't put a star here, but if I say print of star.found, then it's going to expand the found list into the values, and it would be the same thing as, say, printing 2, 4, and 10. That's what I'm doing. But if I if I put square brackets around this, then it's printing a list which contains 2, 4, and 10 rather than 2, 4, and 10 as values. And by default, print uses a separator of a space. So print is going to turn these integers into string representations and put a space in between them. All that's really handy, but I have to use the star, sometimes called splatting. So I'm splatting this array. It's one way of printing out the results. And so if I take this, and so I'm just going to copy solution 1 to subs now. And if we look at this, that is the code that we have here, and I'm printing that. And so if I go back to the window where I can execute make test, then I see I'm passing all my tests. There's no unit tests here, even though this is set up to always run on the program itself to see if there are unit tests to test them. But there's none in here, so there was nothing to find. And it prints, and it shows that I'm passing the other tests that are in the integration file. And I would always encourage you to go read those as well, especially if you are looking for more challenges. So part of what I'm showing here is just some simple tricks. This is important to know if you want to expand a list into its actual values. You can use the splat operator. So here I'm just going through individual lines, what I've shown here, and when it finally returns -1, we know that's when we need to break out. So I point out that this solution would be very obvious to someone who comes from C or maybe Perl. It's a very imperative approach, and there's something here I'm introducing, the idea of state. So this is how data in the program changes over time. And so if you're playing a game or something, an infinite loop is a very common way of essentially creating this a cycle where some input comes in from the user and you respond and change the state of the games, maybe change the picture that they're looking at, or some information like writing tic-tac-toe, which is something I talk about at the end of Tiny Python projects, and I present a way of maintaining the state for that program in a couple of different ways, using variables, using a struct, something like an args, like the class that we use for args. And so a lot of times when you have programs like this that need to maintain state, you have to figure out a way to do that. And so what we're doing here in our program is we have the state here is basically these two variables where we're finding the last position, which we're using over and over again in this while loop, and then this is collecting the results, the found. And it's very possible that there are no results, and so it's important that we run our program on bad input where we don't find the subsequence and ensure that it doesn't blow up. So that's one way of solving this. As you know, I'm going to show you many different ways, and the next one uses the string index, and it looks almost identical, and I'm just going to go ahead and copy solution 2 to subs, so that we can just ensure ourselves, make test. This does pass everything. So let's look at the way this program works. We can look at it either here or here I'll use the PDF. So I'm assigning here this shortcut that I've used before, creating a tuple over here and then unpacking it into two variables over here so that I'm not referring to args dot, which just makes it a little less to read and type. And I'm doing exactly the same thing where I've got my two state variables here, but now my while condition is actually using this test. So rather than writing while true and having a break, the important part of this solution is that I'm showing that this returns true or false. While it's true that subsequence is in the string slice of seek starting at last, then while this is true, then it's safe for me to execute string index, looking at the subsequence starting at the last position. And I'm going to assign overwrite last with the result of that +1, which is what I was doing in the previous solution. If you look, I was having to add +1 to position at 2 different times. So I could have did position +1 here because that's in both instances actually the value that I want is pos +1. So here I'm just doing it in this, I'm adding 1 right away to the index, and then I'm appending this to found. And I don't have to do this break condition now. I don't have to say if this value is true, because it's already integrated into the while loop. This is going to return false when the subsequence can no longer be found. So I could at the end just print. I'm going to show 2 different ways of doing this. I could still just print splat found, but I want to talk about why I'm writing it a different way. And so let's talk about this for a second. This is all of that explanation that I just went through. And one of the things I want to talk about, let's go through this and let me go into, I think I have, found is still here. And if I say, what is the type of found at 0? What is the type of data? That is an integer. And so if I were to try to join found on a string, it's going to blow up because join wants, if we look at help string join, oops, I typed that wrong. It's going to concatenate any number of strings. So string join concatenates any number of strings. And the problem is that found is not strings. It is a list of integers. So the question is, how can I turn those into strings? One way I could do it is a list comprehension. So if I say in for in found, then it looks like that. If instead I say string of in, then it creates 3 strings, 2, 4, and 10. And now I can pass that to join, and I have 2, 4, and 10. That's useful, but I want to show you a few shortcuts. One is that I can always use a map with a lambda instead of in a list comprehension. So that looks like this, and if we take that away, let me just coerce this to a list. I must have forgot that. So that is another way of creating a map, creating a list of strings. I'm mapping into a lambda. Lambda takes in, and I'm calling string on in. But the handy thing, and I use this quite a bit, is if I say list map into just the string function of found, then I get a list of strings. So what's happening is that each member of found, and found again is 2, 4, and 10, each number goes into the string function. So if I say string of 2, I get back the string 2. And so because the string function is designed to accept a single argument, well, that functions as a lambda. So whenever you have any function at all that accepts a single argument, you can use it as the function to map and filter and take while and all the other fun higher order functions that I've been showing to you. So really handy to know about these functional programming techniques. They can save you a lot of typing. So this is why I'm showing yet another way of turning found into a list of strings that you can then use on join. So let's look at a purely functional approach. We're still doing a very manual way of keeping track of this state and then creating this found list, and that's not too bad. But how else could we do this? So let's to start, we consider that we could create something like the while loops. It's creating this list. So we're going through and we're appending to a list. Well, that's essentially a list comprehension. So starting off, let's talk about how we could create a list comprehension. Just going, starting from the length of the sequence, minus the subsequence, because we don't need to go to the end of the sequence. At some point, if seq is this and subseq is at, well, we don't need to start searching at this position, because it's impossible to find the subsequence when there's just simply not enough space. So we only need to go, let's look at this. What is the answer to that? Is 13, and the length of seq is 17. So we only need to go up to the 13th position. So this is one way of iterating over the values in that range. These are the positions where we can look for our subsequence. So using that, I could look for the subsequences at that position, and whenever it's not negative, it's going to return a positive value. Well, whenever it's not negative, that's a position where it can be found. So I only want the positions where it's not -1. So I could do that with a filter. We have seen that with filter several times. The lambda here is going to be taking an n, and I'm going to say I want n to be greater than or equal to 0. So what does that look like? That filters out those last three positions. Fantastic. I'm going to show you a funny way to write this, reversing the 0 and the n. That's going to be important because of the next step that I'm going to show you. So this will give you the exact same answer. So we're saying that 0 is less than or equal to n, which is just a different way of writing n as greater than or equal to 0. I show you that so that I can import partial again, which we saw in the previous chapter. I'm also going to import operator because I want to create an OK function, and maybe I could have also called it, greater than or equal to 0, something like that. And I'm going to create this OK, and so OK, for instance, of 0, is that OK? Yes, that's true. Is 1 OK? Yes. Is -1 OK? No. So the OK values are greater than or equal to 0. And one way to write that is to say less than or equal to 0, because 0 has to be, I'm trying to bind the first argument. And so that was the way it needs to be written like this. So in the greater than, if I wrote greater than or equal, the 0 that I want to bind is the second argument. Okay, that's a problem for partial. I need to bind the first argument. So the way to write that is to say 0 is less than or equal to the thing that I'm going to give as the second argument. So that's what's going on here. Partial is binding 0 as the first argument to less than or equal. So using that, now I can write my filter this way. And it finds the non-negative values. Great. So I can also change that to a map. Instead of the list comprehension, I can use a map operation if I want. and mostly I'm just showing you another way to write this. And I'm going to build up because I want to introduce another partial function where I'm going to use seek find. So what I'm doing here is I'm calling seek find subseq on n. Every time I'm executing this map lambda, the first argument is subseq. So therefore, I can create a find function where I'm binding to seek.find subseq as the first argument. So with that, I can now write an even shorter version of my find. And I'm saying filter for the numbers that are okay, finding in my range of numbers, find the subsequence that I'm looking for. And I'm still getting the same answer. However, a couple of problems with the answer. First off, they're duplicated, and they're also not the numbers that I want. They're one less than the numbers I want. So how can I address those? Well, the first thing I can do is I can introduce a set. So we have not talked about sets yet. You can create a set using the set function, or you can, and that creates an empty set. I can assign that to, I'll just assign it to a variable s, and I can say what is the type of s. It is a set. And a set is interesting in that it's unique. So if I say set add a, it has a. And if I add it again, set still has just a. I can only add it once. And if I add b, and then I add a again, set now has just a and b. And sets can be heterogeneous as well, so I could also throw in a number like 10, and so it doesn't matter what the values are, they will only be represented one time. So using that information, I can say set on that list, and it will produce 139. I don't even need the list. The set is going to coerce that into its values. It's going, because remember, filter is a lazy function. So set will consume the lazy function and give us just the unique values. Very cool, but they're still off by 1. I'm going to yet again create another partial function where I'm going to bind to the operator add the value 1. And so add 1 now will give me 1 greater than any number I give it. So 99, 100. And so I can use my add function to then create over the set of values that are okay, I want to add 1. And here is that same trick that I'm showing you. Add 1 is a function that needs exactly 1 argument. So I don't have to write lambda n, add 1 n. I can just say add 1. And so now when I run that, I'm getting 2, 4, and 10. There's one last thing I need to throw in. Because of the way a set might be implemented, there's no guarantee that you're going to get the results in a sorted order. It happens to be coming out that way in our limited testing, but it's just a property of sets, things that are based on hashing of values, that they may or may not be in some sort of a predictable order. So therefore, it's really best if I call sorted on them. And because, and we've talked about this in Python, if all the values of a list are integers, the values are going to be sorted numerically. If all the values are strings, they're going to be sorted lexicographically. And so it's a very, very bad idea to mix strings and numbers or any types in a list. Lists should really be homogeneous. And so we know that they've all been turned into, that they are all numbers, that they've been filtered, that we've increased them by 1, and now finally we just need to sort them. So that is a purely functional way of writing this. And finally, we're going to have to print it. So we have a bunch of sorted numbers, and we get back into how do we print them? Well, we can actually print star on that all of that function, and we can allow Python to do the coercing of the numbers, and that's fine too. Or we could go back and throw in yet another map of turning them back into strings. But that would need to happen at the very end. We would definitely not want to turn them into strings before we call sorted, because then they would be sorted lexicographically, and it would be like 10 would, you don't want to do that. Make sure you're sorting them numerically. So here is what a purely functional approach looks like. I'm going to copy solution 3 to subs.py, and we'll look at that. And so all of that talk through the REPL is what's going on here. Unpacking our values, creating the range that we want to use, creating our OK for the ones that are not negative, creating our find, which is partially binding seek.find to our subseq. We're creating our add one by binding a partial binding of operator add with one. And then there is the final solution, sorting, adding one, doing a set over the filter of finding. Kind of a mouthful, but it does pass. Let's make test. Make sure that it passes everything. And so this is another valid way of writing the same function, the same program, but now we're not maintaining state. We've combined a bunch of functions that will filter out the bad values and then give us exactly what we want. So this solution would probably be pure gibberish to someone coming from a purely C background, but if someone had programmed in Haskell, they would immediately understand this. It is a purely functional language. So completely different approaches to programming paradigms that you can both accomplish in Python. And then, of course, there's the entire object-oriented paradigm, which I'm not going to cover at all because if you'll believe this, I find it confusing. And if you find this confusing, you may think I'm a bit nuts. But I'm just trying to show you various ways and let you choose what you think is best for you. So that the next solution it really bears to a lot of what we do in bioinformatics. And this is really probably a lot more performative and easier to understand, and that's using k-mers. So we've already talked about just a little bit here about k-mers in the last chapter. And if we go into our REPL, and we're going to say, so we have seek is that, and we have subseq is this. So what we want is where k is equal to the length of the subsequence, and in this case it's 4. So we're looking for all the formers, and so we can say the positions where the subsequence is found, that's what we're looking for. And so here are all the k-mers that are in our sequence. And we talked about in the last chapter that the number of k-mers is equal to the length of the sequence minus k plus 1. And that is what's going on here. This is the number of sequences. Let's just take that part. Well, let's look at, this is the number of k-mers in our sequence. And that is a lazy function, so I have to do a list to coerce it. But these are the positions where we could start to find our sequence, and that corresponds exactly to our range before that we saw that we created manually with the list comprehension. So with that, so here it's almost exactly the same. So with that, this is the number of k-mers, and so what does k-mers look like? These are the k-mers that are in our sequence. And so we could say, is subseq in k-mers? Yes, it's true. Doesn't tell us where, but that's important to know. And again, I want to stress this, that we're using in here now for list membership, and we have also used it for substring presence in a string. So it's the same operation syntactically that does actually two completely different things. So what I actually want, instead of knowing just that the k-mer is found, is I want to know what the k-mers are. Well, I mean, in this case, it's a little silly. I know that they're all going to be AT. And that's useful. So I have found the 3 k-mers, but the problem is I don't know where they are. And just knowing which k-mer it is would tell me the position where it is, because this is the first k-mer, and that's starting at the beginning of the string. So if we look at seek, GATA is the first, is at the beginning of the string, and that is my first k-mer. So just by virtue of knowing what number k-mer I've got, I know its position in the string. And I can get that from a function called enumerate. We haven't seen enumerate yet. And so if I were to say enumerate on my k-mers, it's going to create this, again, a lazy object. So I can coerce it with a list. And now I've got a tuple of the position of the value and the value itself. So the 0th k-mer is GATA. The first in position 1 is AT, and that's one that we want. In 2, there's TATA, and then in 3, there's another AT, and in position 9, that's an AT. So those are the answers we want: 1, 3, and 9. So that is a way of I could instead instantiate k-mers to be a listing, enumerating over that range, and now k-mers looks like this. And so what I can say is I only want the ones that match the subsequence. So I can do that with a filter. Now, as we've seen before, filter is built to only take a lambda that has one value. And let's look at k-mers again. Let's just look at the first 3. This is a list of tuples. And so the tuple is going to go in here, and I'm going to call it T for tuple. And it's a terrible variable name, but it's acceptable to me in this limited instance because this is the only place T is going to exist, is right here in this lambda. And it's because it's a tuple, and I'm saying look at the tuple, look at the thing in the first position, and tell me if it's equal to the subseq. And that is going to give me my 3 k-mers with their positions that I'm looking for. Fantastic. So I actually really only care about the first number. I know that the subseq is going to be the thing I'm looking for. I really only care about the 1, the 3, and the 9. So rather than writing a filter, I could write a map. So the map says, given this tuple T, I want the thing that's in the first position if the thing that's in the second position is equal to the subseq, else I want none. And that's going to produce this list that's going to have things that I want, 1, 3, and 9, and a bunch of things I don't want. And why did I choose none? Well, I could have chosen -1 and gone back to using my filter like I had written before. And that's fine, but I'm going to show you an even cooler trick that will get rid of that, get rid of the nones very easily. But first, I want to show you star map. So because I'm having to accept in the regular vanilla map, the lambda only takes one value and I'm calling it t, I would really like to expand that tuple into 2 variables that are named I, which I'm using in this very limited instance for the position. So just as I was saying for I in range, and I to me indicates immediately that's an integer value, and I'm only using it to count the position. That's pretty much the only time I use I. So I know immediately, okay, this is the position of the k-mer and the k-mer itself. I want to unpack those 2 values into variables so I no longer have to talk about t sub 0, t sub 1. In order to do that, I import from itertools star map. And now I can write my lambda with 2 variables instead of t. And the variables are named such that they make sense. So I plus 1 if k-mer is equal to subseq, else none. That's actually pretty readable. Even though, I guess for certain values of readable, right? It's readable to me. Maybe it looks a little bit crazy to you, but it's not bad. That's getting a little long. I'm showing that stylistically I could assign that lambda to a function. And now I'm really getting into like mathematical and functional programming ideas where we start using variables names like f, a, b. So f here is a function. And so I can now say list. Okay, first off, let's just do star map of this and look at what that gives us. That is, so I'm saying star map onto my function k-mers. That is going to produce a lazy object that I can then coerce with list. There is my same answers with the nones, but now my values have been corrected to 2, 4, and 10, no longer 1, 3, and 9, because that's what I'm doing. I'm returning I plus 1 if the k-mer is equal to the subseq, else it's none. I need a way of getting rid of the nones. Again, I could have said -1 and used the filter before, but I want to show you an interesting trick. If I filter on none, for some reason, that particular filter will just coerce all the values into Booleans, and the filter will be give me the things that are true-ish. And none, as we've seen, if I say what is the Boolean value of none, that is false. What is the Boolean value of 2? That is true. So it is, it's a cool trick to know that if you have a bunch of things that can be coerced to Boolean values, that you can do filter none to get rid of the falsy ones, the false-like ones. And so what does that solution look like? Well, let's see, that is the functional k-mer, I believe is the one that I'm looking at. Let me verify. I think it's actually this functional. Let's see, is it this one? Yeah. So this is the one that I'm using. Let me copy that to subs.py. Let me make test, verify that this works. It passes all my tests. And so let's look at what I'm doing here. I'm doing this unpacking, which is the trick that I'm doing in the star map as well. So, this one is actually using the list comprehension. So here I'm getting the k-mers, and I'm saying this is another list comprehension using I plus 1 for I and k-mer, enumerating over k-mers if the k-mer is equal to the subseq. So here I'm writing it using a list comprehension along with a guard at the end. And then I'm printing found. And that, perhaps, if you're more of a Python programmer, that probably tracks for something that looks very, very Pythonic. So that is this solution here, using very imperative techniques, going over essentially the same operations that we were doing, but doing it with list comprehensions and not functions. And here is the same idea written using the purely functional approach that I had here. And so this one is the k-mers functional. So I'm going to copy that to subs.py and I'll run make test. And I verify that also passes. So this solution is using the enumerate. Here is the number of k-mers that are found in my sequence. So for I, for the position of the k-mers that can be found, what I want to enumerate is the sequence starting at I, going to I plus k. So that is the k-mers itself. Something that's going on here is that you notice here that this looks like a list comprehension, but it doesn't have the square brackets around it. So let's just talk about this for a second. This works. And it creates this enumerate object. And part of what's going on here is that if I put this in square brackets, it creates a list. If it's a list comprehension. If, however, I put this in parentheses, it creates a generator object. So it is something that will produce these values if they are requested. So I'm going to call this IT for iterator. And if I say next on iterator, it's going to give me the k-mers. But iterator itself is still just this promise to give them, and it hasn't actually done the work. And we if you'll recall, we programmed an iterator in an earlier exercise by using yield. And it has this special the way it works is that it returns a value from a function and then saves the state of that function at that position. And then the next time you come back and call the function, it remembers the state and yields the next value, and on until you've exhausted the function. And that's what's going on here, is that we've, by virtue of not putting square brackets around this, we've actually created a generator. That's essentially what this is doing. And then we enumerate over that. So let's go back and let's do this. This is also creating an enumerate object. And I'm going to assign it now to iterator. And I'm going to say next on it. And it's now producing the enumerated k-mers. And it's doing it in a way that is lazy. So this would be something that you would want to do on an extremely large sequence. If you do a list comprehension, you are going to have to stop your program right there and set aside the memory required to find all the k-mers in some potentially huge sequence, and then store those in memory before the next line of code executes. When you call this line of code, it executes almost immediately and goes straight to the next line because it hasn't actually created all of the k-mers in your sequence. It's only created an iterator that will provide them to you when you want them. So with that, I can now say that found is equal to filtering on none star map, where I take those k-mers, and k-mers is now, if you recall, is an iterator that's going to return a position and the k-mer. And so with star map, I can unpack those into I and k-mer, and I'll say, give me I plus 1 if the k-mer is equal to the subseq, else give me none. And then when I filter on none, I get rid of those values. Found is then therefore going to become an iterator of an int that will return ints, because I didn't coerce this to list, right? This filter is going to return another lazy result that can then be coerced at this point in the code to found. So if I were to execute this program on an enormous input, but I never actually executed found, it would run almost immediately. If, however, this was if I were to coerce that to a list, if I were to make that a list comprehension, if I were to put list here or anything, then it would take a long time because it would have to produce all those values. So going back to my introduction of the take while lazy function, that would only consume the values from a generator while they pass some threshold, some predicate. So that is the case to be made for writing these purely functional lazy functions that will only do the work that's required. We have seen iterative approaches, like when we were translating RNA to protein, where in a for loop we said, oh, we found a stop position, let's stop right here. And some of the functional approaches just went all the way to the end of the string. And so this is, there are ways of getting around that. So we don't, so you can either write a very iterative approach, imperative approach, that knows when to stop, or you can write these lazy functions that will stop consuming them when some condition is reached. So we've built up now to finding a solution that uses regular expressions, but as noted in the introduction, normally it finds non-overlapping versions, and we've already seen that. So find iter, as we've seen, let's import re, and let's do find iter on for the subsequence on that, and that is going to create something that's an iterable. I can call next on it and next on it, and then until it's exhausted, so it has found two positions, but we needed to find more. Find iter is very useful. Again, I'm going to stress from a performance standpoint that if this potentially finds 1 million hits, then you're only going to be consuming them one at a time, and you don't have to set aside memory to store 1 million of them. This is like several solutions that many chapters back, when we had a solution that only stored the last thing that we were looking for and didn't store all of them. So I have a note here that the solution is actually simple once you know what it is. And when I was writing this, I didn't know the answer. I was like, surely there's a way of finding the answer to this. And a lot of it, when you're doing searches over the internet, is just knowing the terms to look for. So, we're using a regular expression, but that's often shortened to regex. So when you're looking over forums and people talking about these things, do you search for regex or do you search for regular expression? Most people are going to write regex, and then I have to look for regex overlapping patterns, and then that turned up some things, and then I had to go searching. Obviously, I wrote all of this well before agentic AIs that could probably write this for you. And there's just still something in me that hasn't yet embraced those tools. And so I still would prefer to find answers and to think about them and mull it over and run some code in the REPL and figure this out on my own. But I'm of an older generation. So it turns out the problem is that the regex engine consumes the string each time it matches and then starts at the next one. And the solution turns out to be something called a look-ahead assertion, which if you're not familiar with regular expressions, you've probably never heard of such a thing, and you would not know to do a search for, oh, what I need is a look-ahead assertion. How do I write that? So once I found it, this is the way to write it. The pattern that I'm looking for gets wrapped in this extra syntax. It doesn't really matter what the syntax is. It's just the regular expression engine that Python uses. This is how a look-ahead assertion is written. And there are also, this is by note, a positive look-ahead assertion. There are also things that are called negative look-ahead assertions. And then, as you can imagine, there's both positive and negative look-behind assertions. So now that you know that these things exist, you can add that to your vocabulary and perhaps find things like that. So instead of the way that I wrote the iterator, the match before, I'm going to write it like this, using this extra syntax wrapped around the subsequence that I'm looking for. And now I'm finding, let me import, from pprint, import pprint, and let me pprint that. And I get a little bit nicer output. And now it lines these things up, and I can see clearly 1, 3, 9. Those are the answers I need right there. So how do I get those answers? Well, what are these things? Well, there's these things called RE-match objects. And if I say help on RE-match, it will give me a lot of really good stuff to look for. And I see right away, oh, there's something called end, return the index at the end of the substring. Cool. What I actually want is start. So there is a return the index of the start of the substring for that subgroup. Very cool. So I could actually write this list expression, this list comprehension here. And that is 2, 4, 10. That is what I'm looking for. So for match in RE, find iter, what I want is match start plus 1. And I'm doing that over for each one of the values that are returned by find iter. So this for loop is going to consume the iterator here, and put each value, each match from find iter into something called match, and then I return start plus 1. And that is how I get 2, 4, 10. So it's a really straightforward solution once you know what to look for. And now my solution, therefore, becomes something really almost trivial. So once I know that I'm going to import RE, I no longer need any of that. I'm not going to need iterator anymore. And I go here, argparse is all the same, but all of those lines of code, now it becomes one line of code. That is always nice. When I can write just one line of code, make test. Let's see, it's failing. I need to, args is assigned to, right. there must be, I probably unpack it. Yep, right there. 2 lines of code. I guess technically 3 lines of code. Let's try that again, and that is why we have tests. And so this solution is very, very straightforward, really probably far, far easier to read than all the functional stuff I showed you, although I think that stuff was cool, and I think hopefully you learned some tricks that you will be able to use in other projects. But for this, that would be my solution. And let's see, it looks like there's another bench program here, and I'm just going to run it for 10 iterations real quick, and let's just see how bench does, comparing all of my different programs to see which one comes out as the fastest. And I'll let that run for a second. When I wrote the book, Solutions 2 using str.index ran a little bit faster. Let's see how it's going to look this time. Solution 2 str.index is still faster. It is pretty significantly faster than the regular expression solution. And we've seen that many times before. Regular expressions are simply more expensive to use. And so it's a trade-off. It's slower, but it sure is a lot less work on our part and a lot fewer lines of code. And it's probably going to work better. And especially as let's consider some of the going further. So if we were looking for a pattern instead of an actual literal subsequence, then this is probably what we want. For instance, let's say that we wanted to use something called like a spaced seed, where instead of we're looking for AT, we're looking for AT and then anything at all here. Like we could put a star character there to represent, some sort of a wild card. We're looking for AT something T. Now all of a sudden, string matching is probably not going to work because we really have a pattern now and not a literal string. And so there a regular expression would be better. Or let's say we had something like an SSR, which is a microsatellite. We're going to be given something like GA26, which means GA repeated 26 times. And so are we going to take this and parse it out ourselves and write out GA 26 times and then look for that specific substring? Or are we going to maybe translate this pattern, the way it's normally written, into a regular expression, which is not hard to write? To say GA repeated 26 times, that would be far easier to just turn this into a regular expression and use the RE engine. Another way a repeat could be written as GA and then 15 GTs and then GA twice. This would be pretty complicated for us to translate that into a literal string. It's probably a lot easier to translate that into a regular expression and then use the regular expression engine. Also, how would you find IUPAC codes? I say here R represents either A or G, so the sequence ARC can match either AAC or AAC or AGC. So again, that probably gets into a regular expression, which could be written pretty easily using a character class there in the middle. So those are some reasons why, even though the regular expression solution is slower by quite a bit, more than 2 times as slow, that might be a reason not to use, to go ahead and use it. So in this chapter, we talked about str.find and str.index, and we talked about some imperative approaches that used a loop, a for loop with str.find, and we had a manual break in there, but inside of an infinite loop that we used with while true. But we turned that, we used the while condition using on as long as the index, as long as the string was in the string, then we found it could be used with index inside the loop. So those were a couple of imperative approaches. Then in the functional approaches, we had to consider how to use a set to create a unique collection of the values that we were looking for. Because we had already talked about k-mers and the fact that k-mers are subsequences, we realized that the k-mer solution was definitely a good way of going about finding the subsequence that we were looking for. And finally, we talked about regular expressions, but the fact that they don't find overlapping sequences, and therefore we had to figure out something called a look-ahead assertion. So with that, we have that is this chapter.